Talk to her, I'll see. Okay, but first things first, we're not even close to that, so let's start from reminding ourselves what we did last time. So last time we were talking about Feynman diagrams. And perturbation theory. So specifically, we looked at this phi to the fourth field theory with the real scalar field. Okay? And then we added an interaction. And we said that like Feynman diagrams are a tool to computing perturbatively around some free model. Okay? So specifically, this is what we would call L0, this is what we would call L interaction, and then we can look at all sorts of correlation functions, but the simplest one we can imagine is computing this kind of correlation function, which we will denote by d of q. Okay, this is the bosonic correlation function, and we discussed the fact that we can write this as a field integral d phi sum over m 0, not m, it's n minus 1 to the power of n over n factorial s interaction to the power of n e to the minus s0. And then we can okay, then the general philosophy of perturbation theory would be to divide things into powers of lambda, to say that d of q is something like some power series L lambda to the L dL of q. Okay, and then we assume that this power series gives us some sort of analytic function which we can somehow guess from this sum. This is the philosophy behind perturbation theory. Okay, whether it's convergent or not convergent. That's what we're going to do. So then what I showed you last time was we said, okay, let's consider the powers we can look at. So the lowest power was so the lowest power is n, say, equal to 1. Okay, then we have some sort of expectation value. Jesus, you didn't stop me. This is of course wrong, right? Why is this wrong? No, this is like a thermal average. Let's say it's
lambda.
Okay, that's another thing. No, the point is that this is supposed to be a correlation function. So these fields should appear here somewhere. And also we need to indeed normalize. So it should look like 1 over z, the functional integral over phi. Then we have phi q, phi minus q. And then we have this infinite series. Okay. So then at n equal to 1, just to remind you, for example, we would have something like, phi q, phi minus q, and then this guy is something like an integral, say, dk1, dk2, dk3, dk4. All of these guys are 2 pi to the 4 times delta of k1 plus k2 plus k3 plus k4, right? We would have minus 1, that's also there. And then we have lambda over 4 factorial. And then we have phi of k1, phi of k2, phi of k3, and phi of k4. Okay, and then we can use Wick's theorem. So basically, there are two very distinct ways we can. Okay, so Wick's theorem tells us that any n-point correlation function, and we showed that last time, you can break into a bunch of 2-point correlation functions. Now there are two very distinct diagrams that we can consider. We can make contractions like this, and then, I don't know, something like that. Okay? Which would look like this and that, right? Or we could equivalently connect, say, this guy to here, this guy to here, and these guys, which would look something like this diagram. Okay? And then so here, for example, we have something like Q, and then some internal momentum. We can call it, say, K3 if you like, because it's one of these guys. And here we just have Q, and then this guy would be, I don't know, like K1, and this would be K3. We want to read the diagram. There are no arrows, by the way. In a moment, we'll have arrows when we get to complex fields. But for real fields, you draw them without any direction. There is no meaning for an incoming or outgoing. Okay, and then this kind of diagram, we can describe it. So what it actually, the way we can interpret this diagram is that these lines here are kind of incoming and outgoing. They connect to the fields that we want to compute the expectation value on. And this, these internal momenta, what is known as undetermined momenta. This is a momenta that, you see, this K3 is not something that we can determine based on momentum conservation, and therefore we need to sum over it. So this eventually becomes some integral d3k over 2 pi, d, let's call it d plus 1, d plus 1, and then we have, say, d0 of this k. Okay, and then there is a lambda here. Okay. Now you can ask where this 4 factorial went, and it went because, if you think about it for a moment, there are actually 4 different ways of distributing. Wait, sorry. Now we can actually count the combinatorial factor. So in principle, there should be a 4 factorial here. But then we said that there's another parameter which we denoted by Q. Okay? And Q is all the different combinations in which we can contract these guys. And yeah. So let's see. Yeah, so there might be a factor of 1/2 here. So in principle, we know that this guy, say I choose one of these guys, so it can connect to any of these 4. So that gives me 4, and then this guy can connect to any of the 3 that's left. So that gives me 4 times 3, right? But then these two, it doesn't matter if I connect this to this or this to that. Okay, and that's very important. And the way you can view it is you could imagine that you denote this by 1, 2, 3, and 4. Okay? This is not the same combinatorial arrangement like, say, 4, 1, 2, 3. Okay, it's also not the same combinatorial arrangement like, say, 1, 3, 2, 4. Okay, these are not the same. But it is the same as 1, 4, right? 3, 2. These are the same. There is no difference between them. In fact, the fact that I flattened this diagram to a 2-dimensional sheet has no meaning. I can take this thing and rotate it. It's still the same diagram. It doesn't matter. These directions have no meaning. And therefore, it tells me that I only have 4 times 3. So in this case, Q is 4 times 3, and I'm left with a factor of 2 here. So actually there's a factor of 1/2 in this diagram. Okay, and we call this parameter, we said that Q over 4 factorial is what we denote by S, is in this case 1/2. Okay, and then we wrote these Feynman rules. We wrote this Feynman rule. And they list something like this. Each propagator is by the way, here I didn't write these external Green's function. I can add them, they're trivial. So in principle, there's d naught squared times q. Okay? 2. Each vertex, like this, is equal to minus lambda P. What is that? I know. Okay. Okay. 3. Impose momentum conservation on each vertex. 4. Integrate over all undetermined momenta. And then 5 was figure out the symmetry factor. Okay. So then I stopped last class. We looked at a few examples. So the first example we looked at was this example. So we spent some time on this example. And then we saw that we saw a few things. We saw, first of all, that when we take down these powers of the interaction, there is this n factorial. And we saw that the n factorial always cancels between the different ways in which we can arrange the vertices. Like, you see, there are basically 3 copies of this vertex in this case. We could put, the first one here, the second one here, and the third one there, or the other way around. This we don't need to worry about. It always cancels with a factorial, and this is general for all models. Okay? Then the second thing is that we have this 4 factorial guy. So in this case, we have we compare things to 4 factorial to the third, but we want to understand what is this Q, or S, if you like. It's the same thing. And that will come by, the best way to do it is to calculate which kind of switches that you make don't make any difference. So, if I denote this by 1, 2, 3, and 4, then you can see that the switching between 2 and 3 doesn't make any difference. So that's going to reduce 1 factor of 2. Okay, now here, if I write 1, 2, 3, 4, then again switching between 2 and 3. So that's one thing. So I can switch between 2 and 3 and it doesn't matter. Then I can call this 5, 6, 7, and 8. And then here you see there is another thing that I can. So first of all, of course, switching between 7 and 8, exactly like switching between 2 and 3, is the same thing. Yeah, so that's one thing. But another thing is that switching between 2 and 3 and also between 5 and 6 also removes a factor of 2. So I counted 2, 2, 2, and another 2. So that gives me what? Did I miss something? It's supposed to be 1 over 8. Maybe I mixed it up.
2 times 2 times 2 is 8.
Yeah, that's true, but I didn't. Let's look at it again. Let's denote these guys. So let's call this here the internal momentum is Q. This is P, and this is L. Let me wipe out these guys. let's work through this carefully. So we said that in the Q, in this Q guy, exactly as before for this diagram, okay, we get a factor of 1/2. Now, in principle here, we also have a factor of 1/2. I see. Different ways to place contractions in P vertex. Oh, I see. Okay. So yeah, so what I said before wasn't exactly correct. Here, L is exactly like Q, because I can just rotate it around. But P, I can't just rotate it around because this, the vertex, this vertex here, kind of, it depends, you see, how I contract, you can think about it like this. It's like, let's say this line, and this line, and this line, and this line are 4 phi's. So I can basically take this. So let's say this is 1, 2, 3, and 4. I can just put it like this, place it like this, place it like this, and every one of these configurations is different, right? Because you see, I can have this. Okay, maybe I'll draw it. So I can basically have 1, 2, 3, and 4, which would be 1, 2, 3, 4. Then I have 3, 1, 2, 4. Then I have 4, 3, 2, 1. And then the last one would be 1, 4, 3, 2. Right? And each one of these are not equivalent. You can't compensate with any of these rearrangements with twisting this around. Okay? But what you can do, 3, what you should, what we can do is you could simultaneously yeah, maybe the best way to do it is let's actually write these two vertices. So let me do this. Basically, I know I'm very confusing. I want it to be clear. So let's say this is 1, 2, 3, and 4. And then this is like 5, 6, 7, 8. Then we have something like phi 1, phi 2, phi 3, phi 4, phi 6, phi 5, phi 6, phi 7, phi 8. And now we want to find, so we have 2 external lines. So, I can choose, so I know that the L vertex, this guy is going to connect within itself somewhere. And this guy is going to connect outwards. So I can choose, this thing, I can choose any of them. So it's going to be 4. And then I'm going to choose the second one. The second one is going to be 3. So just its connection outside is 4 times 3. Okay, so these guys, they connect outwards. Okay? Now,
Symmetry between
what?
The first symmetry between the other two. because you can switch, right?
Yeah, so now, okay, so now the point is I can choose which ones I'm going to connect here. So I can choose either this pair, this pair, this pair, or that pair. So that gives me a factor of 4, right? Again, I can choose to connect this and that. Sorry, I can connect, I can choose any of the 4 and then connect it to any of the 3. So then I get another factor of 4 times 3. You understand? So then I chose these two. And now I have this. So I can choose this. So I know I need to connect. Sorry, I took 1 and 4. Okay, never mind. Let's call this 4. There's 2. So then 4 connects to 5, and 3 connects to 6. Okay, good. So now this thing, I could have chosen to do it this way, okay? Or I could equivalently,
There's a symmetry.
yeah, I could equivalently done this to that, and this to that. Okay, but because of the shape of the diagram, this has to be a connection between vertices. So 1 to 4 is one vertex, and 5 to 8 is the second vertex. Okay, so now let's see. So that gives us times 2. Times 2. Is there any other way I could have done it? 3 to 6, yeah.
Well, it's like, maybe it's not the same, but it's like 4 factorial squared, and then you need to divide by 2, and you don't want to come twice. So it's not
It's like 4 factorial.
yeah, if I think about it, like 2 separate little bubble, just bubble,
Yes.
4 factorial. And I have 2 bubbles.
Yes.
It's 4 factorial squared, but I don't want to count twice, so we need to divide by 2. It's not the
I'm
same.
not sure I understand, but
Because this is very confusing.
yeah. Maybe it's not a good way of explaining it.
There's a method I saw in Stack Exchange.
There's what?
A method I saw in Stack Exchange.
Yes.
So basically, the external lines are distinguishable on all, and like the internal lines are indistinguishable.
Yes.
So you start by a certain external line, then you count all the ways that you can connect it. So here basically it's 3 times 4, because and then,
Yeah.
And then
We're talking about just this segment.
Yes.
Okay,
Mhm.
okay. So let's
So this and this we already said it's 4 times
4
3
times.
because because
It's the
you
same
can
as the-
connect any of these 4 and then any of the remaining 3. So I took 1 and 2. Now I'm left here. I need to connect internally also with the 5. So I can choose any of them, any of the 4, and connect it to any of the remaining 3. So that gives me another factor of 4 times 3. Okay? And then I have 2. Okay? Why do I have 2? Because this internal vertex I can connect in these 2 ways. Okay? Now there is just one more symmetry which will reduce this number of 2. That's the point. Now what is this symmetry? The symmetry is some mutual exchange of, let me tell you, one moment. So it should be exchanging. Let me see, 7 and 8.
Isn't it the same as the example with we did before, when you exchange everything? Because
So you're saying I can take the whole thing and flip it.
yes,
So that would be 4 and 3. Yeah, that's like exchanging 4 and 3, but then also
5 and
exchanging 5 and 6.
and also 7 and 8, but that's it.
Also 7 and 8, yes. But where did we count this? Okay. Yeah. Yeah. So, exactly. So maybe that's the best way to think about it. That I can take this whole thing and flip everything together, it goes back to itself. So that gives me another factor of 1/2 because of that thing. So eventually, now this guy gives 4 times 3 as before. So we have 4 times 3 times 4 times 3 times 4 times 3. And we should compare that to 4 factorial cubed, and therefore you get 1/8. That's how the 1/8 works. Now, I apologize that this is highly confusing, but I promise you that this is it's only super confusing for the scalar, the real scalar field. But once you go to complex fields, we'll do that in a moment, it becomes much simpler. But let's do a few examples, a few other examples, maybe it will help both of us learn how to do this properly. Okay, questions about this? Did you wanted to comment something about stack exchange?
Yeah, he has a method here.
Okay.
So the method is you start with your external line because they are distinguishable,
Yes.
and you take the first one, you try connecting it to all the you count all the possible connections, which is to the points, and then you take the second one, and again you do the possible connections. That gives you the same diagram as you have, and then you have the internal lines, and you also count the connections.
Mm-hmm.
And
That's basically what we did. What we did here was exactly this counting. The only thing that was non-trivial is this factor of 1/2. So
I
the
think
1/2 comes from the fact that you see when I say you see, for example, let's start from this guy. When I say that I have here 4 times 3, okay, I'm basically selecting any of this. So I selected 8, and then I connected it to 7. And I counted it as 4 times 3 because I could have chosen 5, 6, 7, or 8, okay, and connected it to, any of the remaining 3, okay. But then I also counted this thing internally with all these combinatorical contributions. But within all these combinatorical contributions, I could have actually chosen another configuration where I didn't choose 8 to connect to 7, but say 7 connected to 8, and then connect all these appropriately, and in a way that in the end would be equivalent, which is exactly switching this, and switching this, all of them.
I think 7 connecting to 8 and 8 connecting to 7 is the same thing because you have a contraction here. It doesn't have
Yeah, that's true. 7, you're right. 7 and 8 is not important. This guy is important.
Yes.
So if I switch this and switch this together.
Yes. Also, I think you could switch between the point of 5, 6, and 8, and 7, and the vertex of 1, 2, 3, 4.
What?
You can switch between the vertex of 1, 2, 3, 4,
Yes.
and 5, 6.
No. That's already counted in this. So there's a 3 factorial, which comes from the fact that I could put the Q vertex here, the what we call this P vertex. The P vertex here and the L vertex here, or I could reshuffle them in all possible ways, and that gives me the 3 factorial. That's not the origin of this. Okay, the origin is this switching. Now, I agree with you, and you can see this also from the diagram, that I can take this and let me think about it for a moment. Because in principle, we're comparing everything to 4 factorial. That's the point. So this 7, 5, 6, and 8, we're counting all the, I wrote them before. There are like these 4 clock states that I can consider, which is like 5, 6, 8, 7, 7, 5, 6, 8, and then I have 8, 7, 5, 6, and then the last one is 6, 8, 7, 5. Now let's see, there should be something which is equivalent to switching all these different combinations that we chose should be compensated
to get to get the symmetry factor, like you divide it in 4 factors.
Sorry, what am I doing? I'm talking nonsense. Forget about this. This is bullshit. This is just 4 combinations and there are many more. What?
To get the symmetry factor, you divide by 4 factorial cubes.
Yes.
Okay. So
Yeah, I'm comparing it because the diagram, you see, every order of the diagram comes with a 4 factorial.
But then the symmetry factor is 4 factorial.
No, the symmetry factor. This is Q.
Okay. Yes.
This is so S is Q over 4 factorial cube, which is 1 over 8. So this diagram will come with a 1 over 8 factor.
This isn't Q. You're missing one of the 4 times 3.
Yeah.
Okay, fine.
This is from this.
Yes.
Okay.
But it's still annoying me that I don't understand where did I double count.
The what?
Okay, again, what was our logic? Our logic was, let's go over it again. So this 4 times 3 is trivial, it's just this step. Okay?
I think what's annoying me, maybe it's connected, is that you split this diagram, and I'm not sure what's allowed.
No, I don't have to split the diagram.
Okay.
I don't have to split the diagram.
Okay.
We don't have to split the diagram.
Okay.
So, you see, the point is that you see these 2 configurations are not equivalent. Okay? So, let's imagine that this vertex has 1, 2, 3, 4 possible combinations.
Okay.
Okay? So I can choose, okay. Let's denote this by 1, 2, 3, and 4, and decide that this line is A, this line is B, this line is C, and this line is D.
Okay.
So I can assign like 1 to A, B, like 2 to B, and so on and so forth. But I can choose it any other way. So I can, the first one I choose, I have 4 different options where I can place it.
Okay.
Then I'm left with 3 remaining ones. I can put the 3 anywhere I want.
Yeah.
Okay. And then presumably, a good way of thinking about it is that you have something like phi 1, phi 2, phi 3, phi 4, and then two of them need to go out. These are these two lines, and then two of them need to connect. So you can decide any of the four and take it out. So that gives you four combinations. Then any of the three, that gives you three, and then you're left with these two. But the point is that it doesn't matter if I connect 3 to 4 or 4 to 3. It's the same thing.
Yes.
So that means that here you get only 4 times 3. And this is this first 4 times 3. Okay? Now we do this guy. Okay? So this guy, what my claim was, that we can basically start from the top, from the 7 and 8. Again, as before, I can choose okay, you know what? Okay, I can choose any of these 4 and connect them to any of these 3. So just this connection gives me 4 times 3. Right? Then where did we get another 4 times 3?
From the 1 and 2. On the
From the 1 and 2, yes. So this 1 and 2 also, how they connect outside gives me 4 times 3. And then I'm remaining with this, but somehow this thing, despite the fact that naively you have these two contractions, they're basically equivalent. That's the point. Now they should be equivalent the same way, here, that you can connect 3 to 4. So it just tells me that connecting 4 to 6 and 3 to 5 is actually the same as connecting 4 to 5 and 3 to 6. I think the way to maybe think about it is that you can, you can think about, because this switching basically is like saying that this part connects here. And this part connects here, or twisting it around.
like the middle.
The middle.
Yeah.
But if you twist only the middle, you see it does look like two different combinations. But somehow it's also important to switch the top. I don't know. Of course, connecting 7 to 8 is the same. Okay, I don't know. Maybe I'll have to get back to you exactly on a rigorous way on how to
Like
get this one half. But
Yeah.
what?
It's the same as how we explained the first example, where you have 2 and 3, and when you switch them, you get the 1/2 factor. It's important
Yes,
to
it's
switch.
exactly the same, but the difference is that here it's obvious also from the contraction.
Yes.
Because contracting 3 to 4 is exactly like contracting 4 to 3. So it doesn't matter. So it's not like you really have two combinations. So you just get 4 times 3. But here it does look like we have two different ways to contract. You see, you have this one and this one, and they look different. But somehow they become equivalent if, I can switch 3 and 4,
I think it's like
and switch 5 and 6.
But you do get the factor of ×2 from.
Oh yeah. I think this is the point. The point is that you can switch these and switch these.
Yes, exactly. And then it's
Yeah.
the entire middle part.
Yeah.
That's what.
It's like saying I'm counting twice.
Yes.
So I'm dividing.
Yeah. And another way of thinking about
Okay.
No, the reason you divide by 2. Okay, how do I explain that? We divide by 2.
Just for me, the 2 is more trivial than the 1/2.
This 2.
Yes.
Yeah, the 1/2. Yeah, it's the only part that's not trivial. Okay, let's not spend the whole lecture on this. I'll get back to you and try to find a more rigorous way of deriving this. But let's look at a few more examples.
I think the stuck answer is like kind of rigorous.
Is what?
It's rigorous and it gets you the right answer.
And what is the answer?
8. What you go.
Yeah, but
How?
Again, but what is the algorithm that I need to do in order to always get the right answer?
Is just like start with external
Yes.
external point.
Yes.
Count all the ways it can connects to an internal point,
Yes.
and then go to the next one like for example here. So let's take the left one. Okay, the
Yes.
left one can connect to 3 times 4 options because on each vertex it can connect to four options, right?
This guy can connect in 4 different
Ways
ways.
times 3 vertices.
Okay.
And then the right one can connect only to 2 vertices because it can connect to the same one that the first
You
one.
already chose. Okay.
Yeah. So you have 2 times 4, right?
Okay.
Now to connect the two vertices.
So 4 times 3 times 4
4 times 2.
times 2.
And then you have 2 vertices that you need to connect. That's the middle. No, like
This and this.
the 2 vertices that you're already connected to.
This.
Yes. So the ways to connect them is 3 because you can choose 3 lines from the left one and 3 lines from the other one, right? So it's 3 times 3.
3 that are left.
Yeah,
Not
exactly.
choosing this.
Yes.
So where did this 4 times 2 come from?
Because you already chose the first vertices, the vertex, right? The left line, the left external line connected to the first vertex.
This one.
Yes. So the second one have just 2 vertices left because it can't connect to the first
Right.
vertex because of the way of the diagram looks.
But we already considered the change of L and Q and P. It's when is the
Yes,
n factorial of the
yeah.
exponent.
No, so in this way you don't.
You don't count.
Because then you take the number that you get and you divide it also by n factorial. But it gets you the right answer. So okay, so then you have 3 times 3 because each of the 2 vertices that you chose at the beginning have 3 left lines that you can connect.
Let's do this. Let's meet,
Okay.
maybe next week or something, and you teach me, explain to me, and maybe in the beginning of next lecture you can give like a 10-minute explanation on how to do this. But on the go, it's a bit difficult.
Okay.
Okay, but I'll still show you a few examples. So another example is this example. So this is like a single vertex where we fully contracted it. So this guy, it comes with, so we need to compute, because we have only one vertex, it's q divided by 4 factorial. Okay? So we can write like phi 1, phi 2, phi 3, and phi 4. And then, I can choose any of the 4 connected to any of the 3. Right? So I have 4 times 3.
What is this in this case?
Like you have 3, q is 3 and then 1 over 8.
Q is 3.
Yeah, q is just 3. Because you can contract phi 1 to either phi 2.
So you're saying I can choose
Either one of them, and then once you choose one, all the other choices are chosen because the other couple must be.
So why isn't that 4 times 3? I can choose any one.
Yeah.
You're saying I can choose any one of them that gives me 4.
Free, because there are other 3 options.
You're saying I can choose this guy, this guy, this guy, but then it's already chosen because
Yes.
I'm going to.
Because it's like it's not exactly pairing; it's like contractions. Because, like, let's say the 4 that you think of, because like you can start from phi 1, phi 2, phi 3, phi 4, but actually it doesn't matter because because it gives you the same contraction and it's
Yeah.
not external.
Yeah, you're saying naively, I would say I can either choose to start here, 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 or here, and then connect to any of the three. But one of these options is going to be equivalent. Like if I chose phi 1 and connected to phi 2, it's equivalent to choosing phi 2 and connected to phi 1. So that gives me a factor of 3. And then this guy is already chosen. So that gives me 3 over 24, which is 1 over 8. Okay, and then the last example I have is this one.
You can also see this from the symmetry of the diagram.
This
Yes.
3, because you
You
can.
can either flip one side or flip the entire thing.
So I can flip this.
Mhm.
I can flip this.
No, but flipping this and flipping this would be equivalent. So you either have to flip.
No, I can flip this.
Yes.
Only that. I can flip only this,
Mhm.
and then I can flip the entire diagram. That's what you're saying.
But
And that gives me 1/2 cubed.
So what I'm saying is that I think that flipping the right side and the left side might be.
No. I don't think. I think it's completely fine because here I have like 1, 2, 3, and 4,
Right.
and I chose how to do the contraction.
So it's like 4 choose 2 and you divide by half. You can
Yes.
deconstruct.
Mm.
But it's very easy after you know the answer.
Yeah. It's
Yeah,
tricky.
that's the problem.
It's tricky. Okay, and here what we have is here we have these. You have something like 1, 2, 2, 3, 4, and then we have 8, 5, 6, 7, and then you see the point is that we can rearrange these 3 lines in any way we want, and these 3 lines in any way we want. So this means that in this case, Q is equal to 3 factorial squared, I think. So, and therefore S is equal to 3 factorial squared divided by 4 factorial squared, which gives a wait a second. Oh, sorry, no, that's not the right way to think about it. Sorry. Each one of these gives me naively gives me 4 factorial, but then I need to think about the combinations which are equivalent. So it's pairings. So okay, let me explain it. I think I have a better way of thinking about it. So let's denote this by 1. Sorry, let's denote this by 1, 2, and 3, and this by 1, 2, and 3. And then each pairing I can denote, I can denote like the pairing I drew is like 1, 1, 2, 2, 3, 3. Okay? But then you can convince yourself that you have 6 different ways of arranging this, which is, 6 factorial. 3 factorial, right? Because you can do 1, 2, 2, 1, 3, 3, right? And 1, 3, 2, 2, 3, 1, and so on and so forth. And all these different pairings are equivalent. Okay? So they give you, so then you have that Q is 3 factorial. No. It's so Q is 4 factorial Q squared divided by 3 factorial. I think this is the right way to think about these diagrams. You naively assume that they have, 4 factorial times the number of vertices, and then you divide by the number of equivalent.
But why is
coefficients.
there 3? why are these pairings equivalent to each other? These are the ones that aren't.
They are equivalent. Well, why not?
Because if you switch one,
Let's. I don't remember this being so difficult last year. It was more prepared. Let's see. So we can write something like phi 1, phi 2, phi 3, phi 4. Phi 5, phi 6, phi 7, phi.
let's say we
Okay,
choose
so
phi
now-
1 and phi 8
Now,
to be the
now we have. So we can choose any of these four to go out.
yeah,
So that gives me 4.
the same with 8.
This gives me 4. So I have 4 times 4 from the outer thing. Now I want to connect them internally, so I can choose. Okay, I can choose any of these 3 to connect to any of these 3.
Yeah, so you choose one, which is 3, and then you
Yeah,
have 2 more.
But here you see it's the same story as before, because you see I can obtain the same. Okay, let me put it this way: any contraction that I can obtain by mutually switching here
and here.
and here will be counted. So you can ask, in how many different ways can I do that? So let's see. So you're saying, for example, these ones are not equivalent. So, but let's see. So what, yeah, let me try and do it to connect it to what I had there. Let's call this 1, 2, 3, 4. And then the first pairing I have there would be 1. Let's call these guys 0. These are like 0. They go outside. And then here I have 1, 2, 3. 1, 2, 3. And then what I have, the first pairing is this, this, and this. Okay? And then in the second pairing, I'm switching between 1 and 2. Okay? So I'm connecting this to that,
And 2 to 1.
but then also this to that.
Yes.
But and then this to that.
3 to 3.
So
I don't think these are the equivalent ones. These are the ones that aren't equivalent, and if you want to find the equivalent ones, it would be having to switch into for example,
no, I think it's okay. I think we're wasting too much time on these symmetry factors. I obviously screwed up completely with this. I'll cover it up next time. Okay. I apologize for that. I didn't go over the class properly. I thought it's simpler than that, and I didn't remember how tricky it is. Okay, so we'll fix this next time. Okay, I apologize. But as you can see, maybe the important lesson here is that you learn that symmetry factors are tricky and you need to work them out. Okay. Now let's write Feynman rules for a complex field.
Can I ask a question?
Yes.
If it was a vectorial field, maybe still a real field, everything will be the same?
So if it's a vectorial field, typically than a vectorial. If it's a vectorial field, then the Green's function typically it connects some index mu nu,
Okay.
and then yeah, I think for as far as this goes, yes, it's going to be
Okay.
the same thing because yeah, if it's a real field,
I think it depends on like the interaction, right?
yeah.
Ah, well,
Here, like
No, but if we have like a 4 fermion, you could have, for example, a vectorial field A, squared, for example. Okay? And then the same thing would hold.
okay,
Okay?
but like in QED, like the vector
Yeah.
field is coupled to the fermion.
So that's the point. The point is that what I'm trying to get to, and I wasted too much time, is that with fermions, all of this disappears. Like there are no problems. Okay, so all these symmetry factors disappear. But obviously I screwed up. So I need to fix this, and I'll do that. Maybe I'll prepare like a note and send you, or next class in the
but
beginning.
the symmetry factor doesn't import it because it's not a real field, right? Not because it's a vector or scalar field.
What did you say?
I'm asking, the symmetry factor vanish because now we're talking about field.
No,
that's
just
not real.
because in the of expanding the exponent, you just don't get any symmetry factor.
No, this is what I'm asking. Why is it because we are talking about vectorial
It's the form
field,
of
or
the
because it's
No,
not
it
a real
has
field?
nothing to do with vectorial.
Okay.
It's the fact that you have a single boson, and it couples to an electron, like a creation operator and a destruction operator. So all of them are inequivalent in the diagram, and there's no exchanges.
Okay.
Okay. Okay, so here we have again like G naught of K is the D naught. D naught is the propagator, but now it has a direction. Okay, because this thing is going to be the correlation between, say, phi of K bar phi of K. Maybe like that. It doesn't matter. Okay? So now it has a direction. Okay, and then the vertex, it has 2 coming in, 2 coming out. Okay? Because I'm assuming that the vertex conserves the number of particles. I don't have to, but this is typically the situation, and this is lambda over 2 pi to the 3d. And then the other Feynman rules are the same. And the Lagrangian we have is now d mu phi bar d mu phi plus m squared phi squared plus lambda over 2 factorial squared phi bar phi phi. And this is our interaction, which we're going to use for perturbation theory. This is the free part. Okay, and here you can see that instead of normalizing with 4 factorial, I'm using 2 factorial squared because I can exchange these two or exchange these two. But I can't exchange between the bars and the non-barred ones. They're not the same. And then just quickly, I want to get to some other more interesting stuff. So let me just quickly state, say I had the same diagram as before, okay, like this, but now everything has a direction, like this, okay. Then you can basically view this as an expectation value. Let's say that this is Q, this is Q, then you have something like phi bar q, phi q, and then you have an integral. So let's call this p, l, and q, and you have an integral over p, phi bar, phi bar, phi, phi. Then you have an integral over l, phi bar, phi bar, phi, phi. Then you have an integral over q, phi bar, phi, phi bar, phi, phi. We're computing this expectation value with respect to the zero field. And then same story. So like this, we know that the L vertex needs to connect. The L vertex needs to connect to the creation operator. So I make a connection like this. And the P vertex, oh, wait a second. Let's not call this, let's call this K. Sorry. K and K, because I already have a Q internally. So then this guy needs to connect to one of these. And then I need to connect between the P and L vertex 1. So something like this, and then one internally. And then both of these guys go here. So this guy goes there, and this guy goes there. And then I have these connections. Okay, so that's equivalent to this kind of contraction. And then the claim is okay, so the claim is as before. We have 3 factorial ways of arranging them. But then in each one of the vertices, I can choose each one of the pair to connect, to be internally connected or outward connected. So I get 2 times 2 times I don't know why did this get so screwed up. Okay, so here, I'll also have to add this. Yeah. Okay, so also here I don't know how to count the symmetry factor in a way that I can explain it to you on the go, so we'll just skip this. But the idea is that what you can see in this case is that you can switch these around, and you can also say flip between like let's say this is incoming and this is outgoing, then you can't flip between these 2 combinations. You can flip like that and then flip, okay? Or you could, so there's only one, so what does that tell us? Let's see. Maybe we can do a simpler diagram first. Let's do it as before, just to see just one. Sorry for being so, so let's say this is K, and this is, say, Q. So we have something like phi K bar, phi K. Then we have phi 1, phi 2, phi 3, phi 4. And this whole thing comes with 1 over 2 factorial squared. So these guys, I have no choice with them. And these ones are barred, sorry. These ones are barred. So what I can do, I can choose to connect. So basically I can choose between these 2. which one will be connected to k. So that gives me a factor of 2. Then this one is already and then I can choose between these two which one will be connected to k. That gives me a factor of 2, and then I have nothing to play with. So that means that I get here 2 times 2, which is exactly like 2 factorial squared, which means that in this case s is equal to 1. Okay, and it turns out that also in this diagram s is equal to 1. Okay, for the same reason, because in each one of these I can choose twice for the bars and twice for the regular phi's. Which one is internal and which one goes out? Okay. Okay, so now let's go to Yukawa theory, which is what I really wanted to talk about today. I'll send a note explaining what you said and I'll correct it. Okay, so now let's move to Feynman rules of the Yukawa theory. So for Yukawa theory, I'm going to assume some Green's function for the fermions. I'm going to assume some real scalar field with some Green's function for and a coupling between phi, psi bar, psi. So this I'm going to call this L psi. This I'm going to call this L phi. And this part I'm going to call it L phi psi. Okay? And this kind of theory may arise, for example, if you have electrons and phonons. Okay? So as far as the Feynman rules go, I'm going to denote the boson propagator with a dashed line. Doesn't have a direction, Q. And this guy is going to be 1 over Q squared plus M squared. So it tells you everything you need to know. So Q, I'm going to assume it includes also time or frequency or whatever. Okay, so Q squared is something like omega squared plus CQ squared. Okay, if we're doing it in Matsubara space. G naught of K, this is the fermion. The fermion is a complex. It's not a complex. It's a Grassmann, but it has a direction. And this guy is going to be I omega. Let's note I omega plus epsilon of K. And epsilon of K can be some generic dispersion relation for the fermions. Okay, I'm not doing Dirac fermions right now, but we could write the same Yukawa theory for Dirac fermions. Here it's just a single band of fermions. And then the last thing is the vertex. So the vertex looks like this. So we have one fermion coming in with K, one fermion coming out with K plus Q, and this is Q. And this thing is equal to minus lambda. So let's see some examples. So, example, the boson propagator. So we could write d of q is equal to an integral now over psi and phi. Phi of q, phi of minus q, sum over m equal to 0 to infinity minus 1 to the power of m, m factorial s phi psi to the power of m, e to the minus s psi minus s phi. Okay? And then you can imagine that you have two external lines coming into the diagram, and then you can do the contractions with different powers of m. So let's look, for example, so you can convince yourself that the lowest non-trivial factor of m would be 2. So this thing, I can think about it as a power series. Then I have, for example, this diagram, right? Plus diagrams like this. Plus, what else? I don't know. You can draw many other diagrams, okay? And now, for simplicity, let's look at the lowest order.
When can you assume that like an electron is not a Dirac electron, but what you call Ben? Like when can you can physically neglect this?
No, that depends on the Hamiltonian you're interested in solving. So, you know, if you're talking about the actual, like, you know, elementary particles in the universe, then you need to assume all sorts of things about them. But say you're studying some material, okay? Let's say a square lattice. So a perfect example would be the cuprates. So one of the materials that people were fascinated about starting in the mid-80s when ITC superconductors were discovered and till this day is the cuprates. And the effective model that people like is like particles hopping on a square lattice. So naively I can write a Hamiltonian which is something like a sum over, you know, k, say minus 2 times t cosine k xa plus cosine k ya c dagger k ck, and this is like a the interatomic distance. Okay, and say you start from this model. This is like your non-interacting model. And now you can ask yourself all sorts of questions. Like you can maybe say, okay, I want to understand the electron phonon problem in this material. So you can add like, so you can try and do everything like microscopically and like really calculate the best you can. But you can also write a theory for the phonons, right? So you can add to this, you know, plus a sum over, say, q, and then you can write something like, you know, h bar omega q, something like a dagger q a q plus 1/2 or something for the phonons, and then you can try and couple. But this field, by the way, so then you could have something like plus, I don't know, like lambda sum over k and q, and then you could write something like, you know, square root of h bar over 2m omega q, you know, a q plus a dagger of minus q, and then couple this to say c dagger k plus q ck. What this coupling is telling you is that the like position of the ion, which is this thing, is inducing a potential on the electrons. It's basically like a density couple. Okay, and now you can attack this problem from different directions. One of them would be to cast this Hamiltonian to a field theory, and then try and solve things in a field theory. And that's exactly what I'm going to show you now. Now, this is just one example, but it turns out to be quite generic because many times in condensed matter physics we have a phase transition. Okay? And maybe it's a good time to mention this, that you know that there is this concept of quantum and classical correspondence. So we saw, for example, that when you when you want to perform thermal average or compute the partition function for a quantum theory, you basically get something that looks like a classical theory, just in one dimensions higher, where the other the additional dimension is this imaginary time. Okay? Now, assuming that your factors, like you're doing a path integral, so you're summing over different configurations, and each one gets a weight which is e to the minus s. Now, if you assume that for your action is always real, and if it's always real, then when you're summing up all these different contributions, they're like probabilities, and it's essentially like a classical field theory. And that means, so in many cases, that tells you that the physics of like phase transitions, stuff you see in materials, despite the fact that the internal degrees of freedom are quantum, it's described essentially by classical statistical mechanics. One of the ways to kind of destabilize this picture is to add fermions to the picture. So fermions are tricky. You cannot always write them, with a real action. It depends, on what you have. If you see, like, if you take a material and you're looking at its magnetic properties, or whatever order is ordering, and you see that the behavior doesn't fit classical statistical mechanics, you sometimes want to just study models like this, take fermions and bosons and couple them, assuming that your underlying fermions are coupled to this order parameter which is fluctuating and stuff like that. So you might want to study a model like this, and therefore it's generic, what I wrote. Now you could have a situation like, if you really want to, like another way of thinking about this is, imagine you're doing regular Yukawa, like in the textbook, and you have Dirac fermions, but then imagine that you have a mass for these fermions, and that you're expanding close to the band bottom where the mass is dominant. Then you'll get exactly behavior like this, where this epsilon of k is going to be k squared over 2m, right? And it becomes diagonal, basically, because you can go to the basis of the mass, the gamma naught, basically, right? And then everything is diagonal, and that's basically the Newtonian or classical limit, Newtonian limit, sorry. So yeah, it can arise from different limits, but it's generic. Okay. So now let's look at the lowest order. So the lowest order diagram is this guy. And let's write it explicitly. So we have lambda squared. We don't have a minus sign because it's second order. Then we have an integral d psi phi. And we have phi of q, phi of minus q. An integral d plus 1 k over 2 pi to the d plus 1. then I have okay. So let me denote this. This is like Q, and then I have K plus Q and K. Okay, I'm imposing, according to the Feynman rules, I'm imposing conservation of momentum everywhere, and this works. Okay, so then I have here again phi of Q and phi of minus Q. Psi bar K plus Q, psi K, psi bar K, psi K plus Q. Yeah, and maybe we can even use your scheme to count the number of ways you can connect it. So this guy can connect to two vertices, right?
Mm-hmm.
That's it. And then this guy has no factor whatsoever. Okay? And then this guy, sorry.
Yes. So for your power potential is trivial always.
Yes. So you see, I can only connect it in one way, so it's 2.
Yes.
And then the 2 exactly cancels with the 2 factorial.
Yes.
So that tells you that basically the symmetry factor here is 1. Okay, and now we just need to think of how to contract. So basically this contracts with that, this contracts with that, and then we need to contract this with that and this with that. Okay. Now there's a small story. Okay, so these guys. Here I'm going to comment that like phi of Q, phi of minus Q is just the d naught of Q. So we get 2 factors of that. Okay, and then this guy psi bar K plus Q, psi K, psi bar K, psi K plus Q. This thing, I need to kind of shift things around to make it into Green's functions. So this guy is equal to minus so I can take this guy through and also this guy through. So I move it twice so I don't get a minus sign. So I have psi K, psi bar K, psi bar K plus Q, psi K plus Q. Okay? But then in order to make this a Green's function, I need to flip it again. So I get minus psi K, psi bar K, psi K plus Q, psi bar K plus Q. And this means that I get minus G of K, G of K plus Q. So what do you see here? Is what?
It will always happen.
Yeah, so you always get a minus sign, but only when you have what is known as a fermion loop.
Mm-hmm.
So let me explain that for a moment, and you can test that later. That like so let me just give you examples. Let's see. So you just saw this one. Then we can have, say, that one, okay? Or you could have, all of these guys are like fermion loops. What is not a fermion loop? For example, this is not a fermion loop, okay? Or, okay? So these guys will not get this minus sign, these guys.
If it was the frequency was on Subaru frequency, it's an integral approximation.
Well, in the limit of zero temperature, it becomes integral.
Okay.
We're actually going to use that.
I think the eraser is.
The eraser is stuck.
Hmm.
Poor eraser. It just shows that this board is not safe and that can squash someone's finger. Okay, so what we found is that this diagram here is equal to so we have lambda squared times d naught squared of q times something we will call pi of q. And this pi of q is 1 over 2 pi to the d plus 1, the integral d plus 1k, g of k plus q, which is equal to minus t sum over omega integral d dk over 2 pi to the d 1 over I omega plus epsilon of k 1 over I omega plus omega plus epsilon of k plus q. And now this thing we can rewrite as, wait, where did the minus come from? There is no minus here. A minus. And then I have minus I omega plus epsilon of k minus epsilon of k plus q. Then I have here 1 over I omega plus omega plus epsilon of k plus q minus 1 over I omega plus epsilon of k. Okay, now these Matsubara sums is something I can do. I can perform these sums because, okay, so here, this sum is obvious. It's a sum of fermionic Matsubara frequencies of this. So this just gives me the Fermi-Dirac distribution at epsilon of k. This guy is shifted by a bosonic Matsubara frequency, capital omega. But that doesn't change anything because if I just shift it by a constant, I get the exact same frequencies and I'm summing over all of them.
Mm-hmm.
So this one will also give me just the Fermi-Dirac distribution. So I have here a sum over d dk over 2 pi to the d n Fermi-Dirac of epsilon of k plus q minus n Fermi-Dirac of epsilon of k divided by minus I omega plus epsilon of k minus epsilon of k plus
So at the limit of omega goes to 0, this is susceptibility.
It's the static susceptibility.
Yeah, it's just the derivative of the Fermi-Dirac with respect to the energy.
Right.
You convert it to an energy integral with the density of states.
Right. But that's not what we're going to do. We're going to keep the frequency constant, but we are going to take 3D. In 3D, basically this guy becomes 3. Okay? And then I'm going to assume that we have a Fermi surface. So what I'm assuming is I'm going to assume that it's circular. I assume that epsilon of k is approximately VF k minus kf. Okay? And therefore epsilon of k plus q is basically VF square root of k squared plus q squared plus 2k dot q minus kf, okay, which is approximately it's approximately VF k minus kf plus k dot q divided by kf. Okay, and here I assume that q is much smaller than kf. Now, why can I assume that? Because typically we're talking about it depends on what we want to look at. Okay, it doesn't have to be this way, but I will focus on this limit, and this limit many times makes sense because if we're talking about a boson, which is like a collective mode, we're talking about something that changes over many lattice sites. And the typical kf is related to the interparticle distance through density. So 1 over kf is the distance between electrons. And if this is a dense system, then we're talking about collective modes that extend over many lattice sites, and therefore this limit makes sense. Okay, but I don't have to look at this limit, it's possible. And then in this limit I get kf d minus 1 over 2 pi to the d. So I'm expanding everything around the Fermi surface. So this d dk basically becomes like a one-dimensional integral in the direction of k times some angle. So I get an integral, a closed integral ds of k, which is like the solid angle integral, an integral from minus infinity to infinity d, let's call it delta k, which is k minus kf. And then I have theta of minus delta k minus k dot q divided by kf minus theta of delta k of minus delta k. I'll explain to you in a moment what I'm doing. And here I have minus I omega minus Vf k dot q divided by kf. So here I made two assumptions. I took the temperature to 0. So when you take the temperature to 0, these Fermi-Dirac distributions become theta functions. Okay? And yeah, that's about it. So now I can say that k dot q is like kf q cosine theta, and theta is the direction between k and q. Okay, q is defined externally, k I'm integrating over. So then if we look at these delta functions, if we look at these step functions, then we have like 0. So this guy is basically 1 all the way to 0, and then it's 0. And this guy this guy is 1 all the way to k dot q over kf. Yeah. Let me see. No, actually, it's the other way around, though. Maybe I should have written a plus here, I guess. I don't think it matters that much. Minus. Yeah. Okay, it doesn't matter. Let's leave it the way it is. I won't confuse you. So this guy goes all the way to here, and then we have minus k dot q over kf. Now, or I can just write q cosine theta. Okay, so only in this region between them, I don't get a cancellation between the two. And the size of this region is q cosine theta, and in this case it comes out negative because this guy is finite in a larger region than this guy. So then this thing becomes minus kf squared over 2 pi squared, the integral minus 1 to 1 d cosine theta of q cosine theta divided by minus I omega minus vf q cosine theta. And this is an integral that we can so by the way, here I did the integral over delta k, okay, to get that. That's this region here.
Why do you call it delta k and not just k?
It doesn't matter. You can leave it. You can leave it as k, and then from 0, and then delta k, which I wrote over there, is like k minus k.
Oh, okay.
Doesn't matter. But okay. So now we can, you see this integral? I can basically use the fact that q cosine theta divided by minus I omega minus vf q cosine theta is something like 1 over vf times minus 1 plus omega divided by omega minus I vf q cosine theta. Okay?
Okay.
So if I plug this in here, there's going to be one integral which is just going to give me minus 1 over vf. Okay? Times 2, because this integral gives us 2. So the first term is basically n0, and the second term is this integral. Now this term gives me a log, right? It gives me a log because the cosine theta is in the denominator. So it comes out like this: 1 minus I omega over vf q log of omega minus I vf q divided by omega plus I vf q. This is known as the charge susceptibility or the polarization function of the fermions. Okay, and yeah, this is this pi. So now we have everything we need. So in the spirit of this perturbation theory, okay, we said that the d of q, what we found is that it's equal to d0 of q plus lambda squared d naught of q squared times this pi. Pi of q. Okay, and I wrote to you what this pi of q is. By the way, I'm sorry for being abusive with the q, but the point is that here the q is the 4 momentum, and here the q is like the size of the vector q. Okay? But it's, okay? And then I have more terms, right? So I could naively interpret this as a geometric series. Okay? So I could naively guess that this thing is equal to d0 divided by 1 minus lambda squared d0 pi, which is also equal to 1 divided by d0 to the minus 1 minus lambda squared pi. So we see that basically our Green's function for the boson, like what we see is that d to the minus 1 is equal to d naught to the minus 1 minus lambda squared pi. This is like this kind of self-energy approach to normalizing the Green's function. And just to connect this to diagrammatics, right now we summed, you know, this plus that. Doing this entire series is adding this plus that plus many, you know, all orders. Okay? So now let's see what can we learn from this. What do we learn? What did we obtain? Conclusions. So one thing is we got mass renormalization.
Can I have a question?
Yes.
What do you mean by n0?
Ah, n0. Good question. n0 is the density of states. It's kf squared divided by 2 pi squared vf. Thank you. Okay, it's basically the density of states.
You know, why is it like, what's the parameter there? Why 0?
Y 0. So first of all, this is a common notation. It's supposed to be the density of states at a certain energy shift, and this is relative to the Fermi surface. It can be denoted, so people denote it by nu sometimes, by rho, or by n of 0. Okay, these are common ways to denote it. It's just density of states. Okay, so the mass renormalization, what do we see from the mass renormalization? You see that there's a constant term here. So we see that m squared of the boson becomes m tilde squared, which is m squared minus lambda squared n of 0. Okay? So that tells us that whatever the boson mass was, just the fact that it's coupled to fermions means that it's going to be shifted. Okay, so this is a physical effect that you can observe. There's a shift in the frequency of the bosonic mode. And you can see that if the coupling is too strong, you can even have an instability, right? Because if the mass becomes imaginary, it means that the mode is unstable.
But then we can't really assume this perturbation.
That's true. That's true. But it does. It is an important intuition because it tells you that. So as long as this lambda is well, first of all, one thing to be okay, Tzvi, let me turn that question back to you. Why? Why can't we use the perturbation theory in that case?
Because
I think what you want to say is because lambda becomes big and we're doing a perturbative approach in lambda.
you took all the terms.
What?
You took all the terms.
Well, I didn't take all the terms. That's not true because there are many diagrams I didn't take.
Yes.
I didn't take diagrams which are known as like vertex corrections like that. I didn't take diagrams like this into account. Okay? Okay? But that's not the point.
Okay.
So why do you think this approach is not... I will tell you that yes, indeed, in the limit where lambda is small, that's typically the limit where this approximation works. But I just want to point out that lambda can still be small if m is small. Okay, so if you're already close to an instability, even in the limit where lambda is weak, it can push you into an instability. But the perturbation theory breaks for a different reason, which we didn't talk about. We'll talk about it in a moment, because if this is satisfied, then the boson itself becomes soft, and it has an effect on the fermion. We'll get to that in a moment. Okay? But, okay. Now that's one thing. The second one is dissipation.
By the way, how did you get this mass normalization?
Oh, that's trivial because you see, okay. So I didn't mention this, but what this equation tells us is that the effective Green's function, or its inverse that goes into the action, is renormalized by pi. Now the constant term in Q is the mass, right? When I take Q to 0.
Yes.
So you see that here I'm going to get m squared minus lambda squared times the limit of pi going to a constant.
Okay.
What is pi going to a constant? Density of states. So here we can use an analytic analytic continuation, and the idea would be that d naught to the minus 1 minus lambda squared pi becomes minus omega squared plus cq squared plus this m tilde squared plus minus lambda squared. Okay, so this guy becomes a real frequency. So we have, let's call this capital omega. So we have omega divided by VFQ times log of so I have omega plus VFQ divided by omega minus VFQ, right? Or I can divide everything by VFQ, so I can write something like omega divided by VFQ plus 1 omega divided by VFQ minus 1. Okay?
Then the analytic continuation is Q go to IQ.
No, it's omega. It's I omega or minus I omega goes to omega.
Ah, okay.
Plus a small,
I
Yeah.
epsilon epsilon go.
plus some small epsilon to push all the poles to the lower half plane. Now, if you look at this expression here, what you find is that you can clearly see that it's not like, okay, so we could, for example, solve for when this is equal to 0, like a pole would be the collective mode. This would be the boson, this is like the inverse Green's function for the boson, so when this vanishes, it basically gives us the eigenfrequency of this mode. Okay? Now you can see here that when omega is smaller than VFQ, then this logarithm becomes complex. Okay, and that means that we have dissipation. So what it tells you, even without calculating anything, I know that in the plane of omega and Q, there is this line, VFQ, and everything below it is dissipative. In this regime, the model is dissipative. And the reason it's dissipative is because in that case, the frequency and momentum of the boson is capable of making particle hole excitations, which are which are close to the Fermi surface. So if you have like a Fermi surface like this, so you're kind of filling all states up to this point, then you have like a small window omega, and you want to make like a particle hole excitation. Okay, then if omega is too big, okay, then you see, then you cannot make an excitation at a very small q because it's blocked, or there is no excitation. It limits it. This is exactly this line. But when omega is small, then at any q, basically, you can find, across the Fermi surface points to satisfy this, and this exactly gives you this condition. It takes it into account. Now, if I do not renormalize the mode, okay, then I basically have this, m tilde. The mode starts here and then propagates into the particle hole continuum. And the point is that all the modes here are going to be not dissipated, and then once they enter into the particle hole continuum, they become dissipated. So we can also read from this perturbation theory when the boson that we took is going to become damped. Okay, this is something we call, it's called Landau damping. Okay, it's the effect where boson is propagating and generating these particle hole excitations, and it's taken into account exactly in these kind of diagrams because the boson is moving, and then effectively it's creating these particle hole pairs which are propagating and then recombining, and the boson returns, and it's propagating and creating these virtual bubbles again and again and again, and that's how it dissipates. Okay?
But he does not tell me how it dissipates. It can dissipate in all kinds of ways.
So what we're we need to understand what we're doing here. What we're doing is we're using perturbation theory to compute the lifetime of this excitation.
Okay.
Okay, so we're taking into account, in this case, all possible particle Hall excitations. And yes, I'm not telling you to which ones, like I'm not specifying which one. If you like, it's kind of like, actually it's not kind of like, it's exactly like doing Fermi-Golden's rule.
Okay.
But then summing over many, many final states, which are all these particle Hall excitations. So I'm not telling you which one. I'm just telling you what is the lifetime for decay. But it's fine, because if you're going to do an experiment, under the conditions of the validity of the calculation we did, you will find that the lifetime is controlled by this. And yeah, I'm not telling you to which one it decayed, because it decayed into many, many different processes.
No, but I mean, also the lifetime. How can I discover if the lifetime depends on the momenta or the temperature or?
No, we just
Okay.
calculated it. Oh, temperature I didn't tell you because I did everything
it's
at zero temperature.
That's
I
okay.
can do the same calculation at
Yeah,
finite
fine.
temperature,
It's
and then I'll
okay.
get the result at finite temperature.
So
But
just
you have
the
to be
imaginary
careful
part-
because the analytic continuation is a bit trickier at finite temperature, but you can do it.
But anyway, the imaginary part of pi, the correction is the scattering rate.
Yes.
Like,
Is
okay.
it's the
Scattering rate times kind of constant.
okay?
Okay.
Yes.
M tilde is not like constant in like I mean, why does it change for Q?
Oh, because there is a dispersion. It's not. This is just the point where it meets zero.
Q
Right, the dispersion is like the solution. If I neglect this term here,
Yes.
okay, then the solution, the eigenmode, the solution for the eigenmode omega of Q, okay, which satisfied that thing is equal to 0, is square root of CQ squared plus M tilde squared. And that's what I drew here. And I'm assuming that C is much, much smaller than VF, which is typically the case because the bosons, they typically don't propagate in a velocity comparable to VF. They can, by the way, I don't know. Depends on the type of boson you're considering.
VF is bigger than the C is the speed of light, right?
VF?
No, C.
No. This is not a. This is a generic boson. I don't know what is C.
Okay.
It's general. If C is the speed of light, then it's out of the question. When we do elementary particle physics or like standard model, then the boson and fermion are both going to propagate at the same velocity c, and then you can have all sorts of symmetries. You have Lorentz invariance and like supersymmetry and stuff like that. But here I'm talking about a generic case. Okay?
So how do you calculate C in general?
How do you calculate C? So, given a material, you can calculate the speed of sound, for example. If you're doing mean field, like say for example you're looking for the effective theory for some charge density wave fluctuation, then you can obtain it from like the Green's functions of the fermions. Like you can calculate it. I'm not saying that it's going to be accurate. You can also measure it many times. Okay?
Where did we get it from the equations here?
No, we didn't. I assumed. This is a model I assumed.
Oh,
Okay? I assumed that we have a boson. So I'll remind you, the Feynman rules we had was that this guy is equal to 1 over omega squared plus CQ squared plus M squared in Matsubara space.
Mm-hmm.
This guy is equal to 1 over I omega plus epsilon of k, some generic thing. And then there is a vertex, which is equal to minus lambda.
Oh.
So I guess we're out of time, but like the next thing I wanted to do, so next time around, what I'm going to do is I'm going to do the fermion self-energy. Then we're going to do Feynman rules for QED. And then I'm going to talk about doing perturbation theory and Feynman rules for a disorder potential. Okay? Then we're going to do linear response theory. And if time will permit, we will choose if we're going to do a normalization theory or something else. Okay? Sorry for the mess today, but thanks to Tzvi who saved the day. And I'll also publish a note and correct the note to reflect that methodological way to compute symmetry factors. But we all learned from it, including me. Okay?
Good. שאלה.
כן.
כאילו אם אני מסתכל על הביטוי מחוק, אבל רגע, כאילו אחרי החישוב של הסכום.
כן.
אז יש לי איזה אינטרמדיאט רק של אפסילון K ועוד Q, נכון? אינטרמדיאט רק של אפסילון K, זה הפרש האנרגיות. וכאילו בגבול, ש-Q הולך לאפס, אני מקבל את הסטביליות.
נכון, זה בדיוק מה שראית, נכון? זה ה-density of states.
נכון, אבל אני שואל אז, למה פה זה לא נראה לי כמו Q הולך לאפס?